All right. So we have seen now the convergence rate of Gauss-Seidel and the Jacobi. Let's do a little bit of analysis. So if we have the iteration matrix, so let's for example take the Jacobi iteration matrix. So the off-diagonal term I just write as L plus U. We have EK plus 1 is equal to this times EK, right? If we know that my E0 is 01, because assuming I have no idea, right, of what my solution is, so I provide a random initial guess, just like what I did. My initial guess in the example was all zeros, so I'm pretty sure that my initial error is order 1, where order 1 is like the order of the actual solution. Okay, so if that's the case, then what is the order of magnitude of EK? Well, if I say this is the Jacobi iteration matrix, let me denote it by J. EK is equal to J times EK minus 1. Right? EK minus 1 is equal to J times EK minus 2. Etc. etc. And I can go all the way to E0. So I will have K of these J's lined up one after each other. So I have J to the kth power times E0. The convergence rate depends on how does JK behave as K increases. And we have said that usually now like what is the magnitude of JK, J to the kth power? How do we estimate it? What does it depend on? Yeah, the largest magnitude eigenvalue, right? Or the spectral radius. So we expect for large K, the magnitude of this is roughly the spectral radius of K to the kth power times 01. And the spectral radius is defined as the maximum absolute value of lambda I. All right, so to understand the spectral radius thing, we can compute the spectral radius of a few matrices. So for example, for Jacobi iteration matrix, we know the J is equal to actually, so if you write it down, it's basically the inverse of this times minus 2's times these times 0's and 1's, right? And these actually cancel each other. The minus 2's, oh, you get a minus sign. The minus sign cancel with the minus sign in the 2, and the 2 becomes half. So what you get is 0's and halves on the upper diagonal and halves on the lower diagonal, right? This is my J. Now if you want to compute this the spectral radius, let's try that. So diag 1's n minus 1 1 1 plus minus 1, right? That's my Jacobi iteration matrix. Oh no, I need to divide it by 2. Yeah, this is my Jacobi iteration matrix, and I can compute I of J, right? That gives me all the eigenvalues. Let's actually plot it. So let's plot I of J to see what it gives me. So it gives me a range of eigenvalues, right? Because the size of the, I mean, the maximum for, okay, so for symmetric matrix, it actually has as many eigenvalues as the size of the matrix. So I should get 200 eigenvalues here. What is the spectral radius? It's pretty much 1, right? If you zoom in, you can see that it's actually not going to be exactly 1. It's definitely greater than 0.998. Now you can see it's actually not 1, right? It's like 1 minus 10 to the minus 1, 2, 3, 4, 10 to the minus 4. So that actually, it's a pretty good estimate of how many iterations it takes us to converge, right? Because let's see, if the spectral radius is very close to 1, let's say if the spectral radius is 1 minus 10 to the minus 4, this to the kth power is this to the kth power. And do you know the approximation that this is approximately e to the 10 to the minus 4 times k, right? If it's like a 1 minus epsilon to the kth power is approximately e to the minus epsilon k, right? That's basically Taylor expansion. And that's kind of why the number of iterations for us to converge is on the order of like tens of thousands, right? Because the magnitude of the difference between the spectral radius and 1 is like on the order of 10 to the minus 4. So that's and basically you can see we get pretty much a minus cosine curve over here. And as your grid size becomes larger, we'll do analysis next lecture. The closest point to the location where the cosine curve is actually equal to 1 minus 1 gets closer. So you get a spectral radius closer to 1, and it takes even more iterations to converge. And we'll discuss in the next lecture, which is on Friday, on the other side of campus, where we had our makeup lecture previously. I think building 3. I don't remember the room number. I'll send an announcement. The same time, 9:30 to 11, we'll have the makeup lecture. We'll discuss how do we defeat this. How do we defeat the problem that as we increase our grid size, the number of iterations has to increase.